Next, I'm going to talk about an interaction between two continuous variables, battery and mass. So I'm going to fit a regression model where the response variable is price and the predictors are battery and mass, and the interaction between battery and mass. And I'm at this part of the regression interactions.r code file. So here is the result of fitting that regression model. And we can see that the interaction between battery and mass is statistically significant. It has a p-value of 0.002. So I would like to be able to estimate the relationship between mass and price at different points along the continuum of battery life. But I can't think about battery life as categories the way I was doing in the last couple of examples. Instead, I need to think about shifting the reference point or 0 point of the battery variable in order to change where it hits 0 so that I can understand the slope of mass in those terms. So the first thing that I'm going to do to illustrate is make a copy of the battery life variable and show you what it looks like when I shift it by a constant. I'm going to calculate 3 versions of it here. The first one is called battery centered, and it's the result of taking the battery variable and subtracting its own mean, the mean of the battery variable, removing missing values. The second variable here is called battery 0 is low, and it's the result of taking the centered battery variable that I just calculated and adding its own standard deviation. And the third variable is called battery 0 is high, and it's the result of taking the centered variable and subtracting its own standard deviation. Adding the standard deviation shifts all of the points of the distribution of battery life upward, so that 0 comes to represent a relatively low point in that distribution. And subtracting a standard deviation shifts those points downward, so that 0 comes to represent a relatively high point in that distribution. That's not always the easiest thing to understand, so I want to show you some graphical representations. I'm setting up a plotting space. Here is a histogram of the original battery variable. This shows the original units of the battery variable in hours. And on the bottom is a histogram of the centered version of the battery variable that I calculated. I subtracted the mean battery life from every value of battery life. And what it did is shift the whole distribution of battery life downward so that 0 now falls right at the mean. These units can be thought of as discrepancies from the mean. A robot with 10 on battery centered has 10 hours above average battery life, and a robot with -10 has 10 hours below average battery life. Then, when I added the standard deviation to the centered version, I shifted the values up, meaning that 0 became a relatively low value. And when I subtracted the standard deviation from this centered version, it shifted the values down so that 0 became a relatively high value. I'm going to show those two histograms now. The top is the battery underscore 0 is low value, and the bottom is the battery underscore 0 is high value. These are the same distribution of battery life, just shifted around a little bit more. So in this top one, I had the centered battery life variable, and I added one standard deviation of battery life to each value, shifting all of them upward by a little bit, so that now 0 is the 0.1 standard deviation below the mean. And in the bottom histogram, I shifted all of the values down by a standard deviation when they were previously centered at the mean, so now 0 represents the 0.1 standard deviation above the mean. I had to shift the whole set of values up in order to make 0 represent a relatively low value in that distribution. And I had to shift all the values down in order to make 0 fall at the point that's a relatively high value in that distribution. Let's remember what shifting by a constant does to a regression intercept. Here is a plot of the regression slope and intercept for the battery 0 is low variable. And here is a plot of the regression slope and intercept for the battery 0 is high variable. You can see another representation of what I did to the distribution of battery life by creating this 0 is low and 0 is high version. The cloud of points is exactly the same, but in the 0 is high version, it's shifted over so that they mostly fall below the y-axis, the 0 point, and in the 0 is low version, they're shifted up so that they mostly fall above the y-axis, the 0 point. The intercept of the regression model is the point where the line hits the y-axis. In the top plot, where I fit a regression model where the predictor is battery 0 is low and the response variable is price, the y-intercept represents the fitted value at 1 standard deviation below the mean of battery life, at this typical low value of battery life. And in the bottom plot, where I've fit a regression model using battery 0 is high to predict price, the y-intercept represents the fitted value of price at 1 standard deviation above the mean of battery life. The two plots shown on the screen show the y-axis at the same location on the screen to illustrate that I had to add constants to all of the battery life values in order to make it so that they would mostly be to the right of the y-axis, and subtract constants from them in order to make it so they would mostly be to the left of the y-axis. So the reference point in the top graph is a low value of battery as a result of adding constants to all the values of battery. And the reference point on the bottom is a high value of battery as a result of subtracting constants to all the values of battery. Here's a version of that plot where I'm showing the points in the same location on the screen. And instead, I'm showing how the axis appears to shift when we add or subtract constants from the values of those points. The battery 0 is low version has its y-axis down here because all the points were moved up. And the battery 0 is high version has its y-axis up here because all the points were moved down. That's why adding a standard deviation to the centered version of the variable makes the reference point be at low battery life, and subtracting a standard deviation from the centered variable makes the reference point fall at high battery life. We're going to use this strategy of adding and subtracting constants from the distribution of battery life in order to strategically shift the 0 point of that moderating variable battery life to understand the conditional slope of the other variable, mass. So here is the regression model when I have price as the response and battery 0 is low interacting with mass. This is the battery variable just shifted over by a constant. So the interaction term is the same as it was before, and the hypothesis test of the interaction term will never depend on this kind of shifting around. But what's key is that the slope for mass now has a special meaning. It's a lot more useful than it was in the original version where battery and mass both had their 0 points at literal 0 units in hours of battery life and kilograms of mass. Now, the 0 point of battery, the reference point, is 1 standard deviation below the mean of battery life, a typically low value of battery life that falls within our distribution of values of battery life. And this slope of mass is the estimated linear relationship between mass and price at that low value of battery life. For robots who are below average on battery life, specifically 1 standard deviation below average, the heavier they are, the less they cost by about 98 cents, and that relationship between mass and price is not quite statistically significant. And I've switched it out for the 0 is high version of battery life to change the reference point, and when battery life is 1 standard deviation above the mean, the association between mass and price is 1.33, and it is statistically significant, indicating that heavier robots are more expensive as long as their battery life is high. So the conclusion that I might make based on my understanding of this statistical interaction, if this data set was real, is that when robots have relatively low battery life compared to average, people are not paying significantly more or less for heavier ones. But when the robots have a high battery life relative to average, people are willing to pay more for the heavier ones. Perhaps heavier robots have more features, but when the battery life is low, people are cautious about the fact that it might run out of batteries and you might have to carry it home. I also want to show you a shortcut to getting those same slopes for mass without having to pre-calculate versions of battery life where 0 is representing high and low values in the distribution. What I've done here is used the I function again to specify that I want to do some arithmetic before including this variable in the formula specification. So everything inside of this I function call is going to be interpreted as literal arithmetic and not as special formula symbols like the plus sign usually is. I did that so that I could scale or z-score the battery variable and then add 1 to it. A z-scored version of a variable has the same distribution, except that it's been shifted so its mean is 0 and its standard deviation is 1. And then adding 1 to it is the same as adding a standard deviation to it at that point, because I made it so the standard deviation was 1. So the result of this function call is that I have a version of the battery life variable where the 0 point is at 1 standard deviation below the mean. Remember, adding a standard deviation shifts all the values up so that they fall to the right of the y-axis, or most of them do, and the intercept lies at 1 standard deviation below the mean. So this is a version of battery life where the reference point is 1 standard deviation below the mean. And when I let that variable interact with mass, I get the same slope for mass that I got when I had the more carefully prepared version of battery life. And when I use my I-scale strategy to subtract a standard deviation from the distribution of battery life to get a version of battery life where the reference point is 1 standard deviation above the mean, and then let that version of the variable interact with mass, I get a conditional slope for mass that's equivalent to when I used my more carefully constructed battery life variable with the reference point 1 standard deviation above the mean. Again, saying that robots with above average battery life tend to have a positive association between mass and price.